So we have these instructions for RISC-V. So shift left logical is used for SLL, and shift left logical immediate. We also have an immediate variant. So we can also specify how many times we need to shift a particular register. There is no NOT operation. We perform NOT operation with X or I, and we will see shortly how we can do that. And whatever the immediate value that we specify, I also discussed when I was discussing add I. So whatever value, constant value we specify, it is represented in 12 bits. Okay? And again, we'll talk about what happens to the upper 20 bits. So let's say AND operation we need to perform. What do you think? What kind of operation in what operators it is going to execute? So AND operation, again, the convention is same. The first register is always the destination register. The remaining two are the operands. So AND operation will be performed between T1, the contents of T1, and contents of T2, bit by bit. Okay? So it could be, I have examples here. Similarly, we can also specify an immediate value. So which format is this? Is a hex format. And how many binary bits are there? 12, because each hex digit corresponds to 4 binary bits. Okay, so this is exactly represented in 12 binary bits. So suppose T1 is this value, and we can have T2 or immediate value 5cc. So you can simply write 5c and c. So here, when you perform operation, the 12 bits immediate data is sign extended. So here the sign is 0. So all the higher 20 bits are 0. Okay? And when you perform operation AND operation, what will you get is 1, 0. It will get 0. And wherever you see both inputs are 1, the output is 1. Okay? So AND operation or OR operation or any logical operations are performed bit by bit. So each bits are ANDed together and the output bit is generated. Okay? Any question here? Yes?
Does it matter if the hexadecimal is signed or not?
No, it's just we are just discussing the representation. You could simply write its decimal equivalent value, and the compiler actually, the compiler will translate that into a corresponding hex. Even if you write a value that cannot be represented in 12-bit, then it has to, it will be depreciated. The upper 20 bits will be dropped. Okay, but we will see how we can represent a value that cannot be represented in 12 bits. Although 12 bits are good enough to represent a larger value. Similarly, OR operation. So here you can simply write 0xDC0, which is D. But here you can see in D, the leftmost bit is 1. And because of this 1, the sign is extended to 20 bits, the remaining 1 bits. Okay? So that's why all these 20 bits are set to 1. Because the value D has the leftmost bit 1. Okay? So I could have simply given it to you like this, 0xDC0, and you need to perform the OR operation. So you need to determine what should be the higher 20 bits, depending on the sign of the value, immediate value. Okay? Mm-hmm.
So you wrote it like that because each set of ones is an F?
So you see, I have written it deliberately here, 0xFFFF DC0, but I could have written it simply like this. 5cc, I could have written DC0. Okay? So D, if you write it in binary, the leftmost bit would become 1. And that represents its sign. And this sign bit has to be replicated here for the next higher 20 bits. Okay? So in exam, you might be given only DC0. You need to determine what should be the value of the upper 20 bits. Okay? So in order to perform the correct OR operation, yes.
Are you going to let us know if it's signed or unsigned?
Unless if it is not specified, if it is unsigned, then you may assume that it is signed value. Otherwise, it will be specified if it is an unsigned number. But in RISC-V or in computer, everything is signed. numbers are considered as signed. Okay. Okay, XOR and XORi operations. Again, they both work in the same manner, except their operation. When both the inputs are different, the output is 1. When both inputs are same, the output is 0. Okay. We can also perform XORi operation with -1. So you can specify like this, -1. So what do you think this operation is? When you perform XOR operation with -1. So -1 is generally represented, you're performing XOR operation with all ones.
It just inverts.
Exactly. It simply inverts if, so you remember this gate. Sorry. So we have XOR gate looks like this. Okay. And how does it work? If both the inputs are different, let's say 1 0, the output is 1. If we keep, let's say, if we keep one input, let's stick to 1. Now, if I set this input to 0, the output is 1. If I set this input to 1, the output would be 0. So see the pattern? It is exactly inverting the input data. So which means that we have implemented the NOT operation. When we keep one of the inputs set to 1 of XOR gate, then we can simply perform NOT operation. Okay? Okay, so what's that? So we can invert bits in a word, which is word is 32 bits. So if we have to perform this operation, like inverting all the bits in T1 and store the results in T0, we would simply write instruction like this. Yeah.
Why can't we just flip our answer?
Flip? How do you flip your answer?
So we get the XOR for like how we normally do it, and then we just flip our result.
How do you flip?
Just
Like
zero.
just like
If it's
who
zero,
you flip the computer?
no, if it's 0, we just do 1 instead.
But how do you do this? There should be an instruction to do that.
Oh, I see.
Yeah. So the instruction is, there is no specific instruction for NOT. So we have this XOR operation that you can use to flip the bits from one register and store it into another one. You can of course store the bits into the same register as well. Okay. So you're performing in XOR operation of T1 with all ones. Okay. So one of the input is set to all ones, and the another, whatever the value of T1 is, the output would be its invert. Okay. Yeah.
Why would you store it with -1? Why not just 1?
So -1 corresponds to all ones in binary. So this is how you represent -1 in binary. Right? So if you were to take its, so first of all, if you are given this number, as same as we have already discussed, if I ask you what is the value of this number, so what you do is, because you cannot keep counting 1, 2, 4, 8, 16, 32, and the last value is minus magnitude. You cannot do that. It would be too much of arithmetic for you. So what you could do is take a 2's complement simply. And how do you take 2's complement? Keep all the bits same until you encounter first 1 from right. Okay, it will remain same, and invert all the bits. So when you invert all the bits, so all will be 0, and this one would be set to 1. And that is equivalent to +1. So which means that if that is +1, then this may corresponds to -1. Okay. Okay, so let's talk about this. What are the bits in T0 after the following instruction is executed? Okay. So assume that what operation we are performing, first of all, whatever the value of T1 is, no need to make any assumption. We are performing an OR operation with all ones, and we know that in OR, if any of the input is 1, the output is 1, no matter what the other value is. Okay, so it means the output is all bits in T0 will be all 1. Okay, any question? Karima?
I think I get it. It's because, like, it's
So first of all, -1, how do you write -1 in binary? It will be all ones, and you're performing OR operation. So in OR operation, if one of the input is 1, no matter what the other input is, the output will be 1. So T0 will contain all ones.